The other type of dislocation is called a screw dislocation. Now, this is just a name because you see, when we talk of screws, bolts and nuts and screws, you know that the movement of a screw is that you go round and round and round, right? When you try to tighten a screw, you go round and round and round. And when you go round and round, then you create shear stresses. So screw dislocations create shear stresses. And therefore, the distortion that is created near a screw dislocation is a shear deformation type, and we give the name of a screw dislocation and so forth, right? So let us go to the next page and try to see. Once you see that diagram, you can always come back to this and read it again. So now let us see. You see, we have this arrangement of atoms. So there are hundreds or thousands or millions of basic unit cells, right? Each cube is a basic unit cell. They are there. Now what we are saying, that suppose on this shaded side, we apply a load from above, or sorry, the other way around, on this white one, on this white side. You see that shaded side is there, but on this white side here, we apply some pressure from the top. We apply some pressure from the top so that some of this material moves down. That material is not moving, that is normal. This portion of the material moves down a little. So now come to the right side and see that, you see, this portion of the material is there. Here we have pushed it. So this front line has been pushed by one distance, right? By one length. And then the rest is a little, the rest is a little, the rest is a little. By now you are back to the normal height. So you applied some load here. Because of that load, some of the material here has been pushed down and some area has been affected. So more push down, less push down, less push down, less push down, no push down. Here the top is at the top again. So you see there is a shearing which is happening, right? This portion of the atoms is being sheared compared to this portion of the atoms, isn't it? There is a shear on this face. There is a shear on this face. So this plane of atoms or this piece of atoms remain the same. This one is pushed down, so there is a shearing action, and this is the face on which the shear takes place. So the Burger's vector B is now there on this shear face. And this type of force, when this is applied, it is called a screw dislocation. A screw dislocation. One plane of atoms is moved relative to the other plane of atoms. So between the two planes of atoms, there is a shear force, right? It is just like a cutting action. If you take a solid piece, if you take a knife, if you try to cut, then you are trying to push, right, in the material. So there is shearing happening at one face, and that shearing, so there is a shearing happening at this face. So again, because of edge type of dislocations which we did on the previous pages, there will be forces which are compressive or tensile. We have forced an extra plane of atoms inside, so it is pushing them outwards. So there is compressive, and if there is pushing outwards, then below this plane they are trying to have tensile force so that they balance each other. But here there will be a shear force, and if on one face there is shear on this, then on the other face there will be shear on the opposite side, so that they again balance each other, right? So this is edge dislocation, this is screw dislocation, and Burger's vector in each case will try to tell us of the size of the edge or dislocation. Here we are showing you what happens. You see this inverted T is an edge dislocation. Above edge dislocation, compression happens. It tries to force here and force here. And below it, to balance this, tension happens. So whenever there is an edge dislocation, there is a compression tension pair. Above it, there is compression, below it, there is tension. But when there is a shear, if you see there is a shear between one plane of atoms and the other, then this is a screw dislocation. So because of shear, there will be shear all around, right? Shear, you know, shear is on this side, this side, this side, this side. They balance each other so that the total cell is in balanced shear. You know it from your Morse diagram and so on. So whenever shear takes place, if there is a square, then shear is on this face, this face, this face, this face, but they are in opposite directions so that they balance each other. Shear on this side balances shear on this side. Shear on this side balances shear on this side. So there is a round, right, all around type of distortion, which is in the case of shear. So edge dislocation, figure A, is a compression tension pair of forces, and screw dislocation, figure B, is a shear type of stresses which are all around the dislocation. Right? There is a mixed dislocation. There can be some type of distortion in the material so that some portion is having an edge dislocation and some portion is having a screw dislocation, and they will be. So we are showing you schematically that here is an edge dislocation. You see, this is an extra plane of atoms above. So this is an edge dislocation. There will be compression here. There will be tension here. Here we have pushed, right, a plane of materials inside. This is outside. This is inside. So there is an screw dislocation here, and all around there are shear stresses. So there are compressive stresses, tensile stresses, shear stresses. We can treat each of them separately and try to solve for them. So at a level where you will be understanding all of this, you will have to solve for the tension, for the compression, for the shear, and then the combined effect of all of these. If you remember in your solid mechanics, or maybe if you are doing it now, you will be doing it later, those who have done it, there will be a chapter of combined stresses, right? And therefore then we individually solve them. We don't worry about the others. We solve only for the tension, only for the compression, only for the shear. And once we solve it, then we will have some vectors in the x direction. We add all of them. Some vectors in the y direction. We add all of them, and then we find the resultant. So I'm just telling you that if you needed to do it at a higher level, then it will be there. But at this point in this course, we are just explaining to you. So line dislocation is a dislocation, line defect is known as dislocation, and dislocation can be edge dislocation, screw dislocation, and a dislocation. And this is a micrograph of a material which has edge dislocation or screw dislocation. So a lot of cross dark areas are there. The rest of the grains are there. On some places there are some deformations, but some places there are combined. So you see, now if you and I are there who are, say, doing it for the first time, we will not be able to understand it very clearly. But people whose whole life is in material science and so on, and especially to those to whom a lot of micrographs of edge dislocation and screw dislocation and mixed dislocations are shown, then they will see that, oh, all these very much dark lines are dislocations, right? And then we compare it with the properties of the materials. That you see, I have a material which does not have all these deformations, and I have a micrograph of that. So I see how does the grains and so on look there. And then on the same material, I have applied some cold rolling or some other major deformation. And then I take the micrograph and I see, oh, because of the dislocations and so on, there is a lot of dark lines and so forth. And then I can compare them, and then I can try to study the effect of these on the material properties. Okay. The next will be planar defects, right? We have 0 dimension point, 1 dimension line, and 2 dimension, which is a plane, right? So if there are any defects in a plane, then we will have a planar defect. I am taking a very small break, so I'll pause here a little. You will not feel it. I will, but I'll take a small break to give me a break, and I will come back and continue. And I'm pausing, and then I'll again start. So yes, we are on planar defects. Now, there are different types of planar defects. You can see here external surface, grain boundary, twin, low angle boundary, high angle boundary, twist, stacking fault, void, precipitates. They are all planar defects. Planar defects. The most extraordinary is free surface or external surface. Now this is very strange. This is very strange. Take any material, for example, your phone. Take the top surface of your phone. They say that this top surface is a defect. Take any material, a cube or a sphere. The top of the cube is a defect. The round surface of a sphere outside is a defect. What is the reason? Why do they call it? If you think, it is simple. You see, if you are anywhere inside the material, not on the outer surface, then take any atom inside. On all sides, top, bottom, left, right, everywhere, there are other atoms. So if you try to dislocate this one atom, all atoms are saving it. They are a safety. So any atom which is inside the material is safe from all sides, because the atoms to its right or left or top or bottom or back or front will have to be affected before this atom is affected. But now look at the top surface. Below it and to the right and to the left and so on, there are atoms supporting it, but above it there is no support. So if you apply any force, then that force directly acts on the free surface. Therefore, we say that the free surface or the external surface is by itself a defect, because it is easier to damage the outer surface than the inner material, which we know. We take a knife and try to cut on the material. The immediate first thing that we can do is damage the surface. Then if we keep on applying a lot of force, then the knife will go inside the material, right? So the atoms which are inside, they are safer compared to the atoms that are on the surface, right? So this is the defect known as free surface or external surface, and because it is a surface, it is a planar defect. Okay, this is the most famous planar defect of all time: grain boundaries. Grain boundaries, right? We have talked of this earlier when we were talking of crystals and grains and materials and so on. We told you that when materials are liquid and we are cooling them, then as soon as the melting point or the freezing point, right, it is the same thing. If you are cooling, it is the freezing point. If you are heating, it is the melting point. So you are cooling the molten metal. As soon as you hit the solidification temperature, then at different points inside the solid, not one point, at different points, some solid starts to form. As soon as a solid is formed, even a very small size, then some crystals have formed of the metal. If you cool it further, then these small crystals grow, right? Now there are many places where these small solids are there, and all of them are now growing. So the grains are growing. They are not one unit cell now. The first time one unit cell formed, then it grew and so on, right?